In fact, we're so much about developer experience that we even published an entire manifesto for developers with our principles for how to build data-driven application in a developer-friendly way. You can learn more about this on datadx.io. But that's not what my talk is about today. My talk today is about real time. And that's the journey that I want to take on you all on today. So first, I'll set the stage for architecting a real-time chat application. Then I'll walk you through 3 different kinds of approaches and their trade-offs for how you can build a real-time chat app. And then we'll walk away with some takeaways. Let's jump right in. You are in a job interview, and this is your interviewer. And the question that he asks you is, how would you architect a real-time chat application? You think about it, and maybe you start with this architecture diagram that we all are familiar with. We have a client, we have an API server, and we have a database. On the front-end side, connecting the front-end to the client, we can do this with WebSockets. And in the Node ecosystem, we have a couple of different libraries that we can use to implement that. Socket.io is very popular. If you're using GraphQL, you might be using GraphQL WS, or another library that's called Socks.js. There are many more of these libraries. You can also implement that yourself. So that's how you can implement the front-end part. That's how you can respond to the interviewer. But my talk today is about the backend side of things. How do you source the events that are coming in on the backend, and how do you know when to emit what kind of event to the connected client applications? So for real time on the server, I want to talk through 3 different approaches. The first one is called application level updates. Then I want to talk about polling. And finally, I want to talk about how you can do this with extra infrastructure that you're adding to this architecture. The application level updates, there, you really let the application server handle everything. Let's walk through the flow of this chat application and understand how it's going to work. Say we have 3 users that are all connected to our API server using this WebSocket connection. We also have a database. And let's say the first user starts by sending the first message, hello, to everybody else. The API server is going to receive that message, store it in the database, and then emit this message to everybody else that's currently connected to it. I have a demo prepared for this, and now that's the part of the improvisation on a different computer. Where is VS Code? Right there. So here, I'm not going to run the demo, but I'm going to very quickly show you the code. On the front end, I'm using a React application with Next.js, where I instantiate a socket object. I connect it to my local host, where I'm running the server with Socket.io. I fetch the entire message history, and I emit new messages via the chat message channel to the server like this. That's the client side. Actually, if you want to see what this looks like, it's pretty much just this. So to be honest, you're not missing a lot that I can't run the demo. It's not super exciting. It's just going to show the chat messages that are being written in one text field in one window, in both windows at a time, so you can kind of imagine what's happening. But the more interesting part that I want to show you here is on the server side, where my entire application fits into one file. I'm using Express. I'm using Socket.io on the server. Here is where I initialize my sockets. And whenever a new user connects, I printed this to the console. And this is the interesting part here, because that's the part that's being invoked when Alice sends the message to the API server. So the API server first writes the message to the database, and then it emits the same message to all the clients that are currently connected. That's exactly what you've just seen on the slides, just in code. So let's continue with our slides here. What could go wrong with this approach? Say we want to scale our application horizontally. In this case, we now have 2 API servers. And our clients now connect to one of these instances, right? So the first 2 clients are connected to the first instance. The last client is connected to the last instance. Well, you can already see that there is no way, if we let the application server handle everything, that the messages that are sent by Alice and Bob are ever going to arrive at Jane and the other way around. So the horizontal scalability of this approach, it just doesn't exist. The second problem that we have is the so-called dual write problem. The dual write problem means that we have a situation where the API server needs to update 2 different data sources at the same time. So it needs to update the database, and it needs to emit the events to the subscribed clients. What if one of these operations fails? It's actually very difficult to recover from that, and that's the so-called dual write problem. So let's draw the conclusions from this. The pros of this approach are that it's fairly easy to understand. I think you all were able to follow the code in the example that I just showed. You don't need any additional infrastructure, but it's not really possible to scale this kind of application architecture, and you also have the dual write problem. So that's not really how we want to implement something like this. Let's investigate another kind of naive approach to the same problem, and that's polling. In this case, our API server will periodically ask for updates from the database. I'm using the same illustration and want to walk through the same flow again to make you all understand what polling actually means. So first, let's assume that we define a polling interval of 1 second. So the API server is going to start. It'll request the new messages that have been sent in the last minute to the database from the database. In this case, we didn't have any messages yet, so the database just returns an empty response. Next, Alice starts by sending a message. The API server writes that into the database. The API server then queries the database for new messages. So we have arrived at the next polling interval. And the database responds with that message that just arrived. And now the API server can broadcast the message. The code for that, in this case, I'm just going to show you the server code. The client code looks identical for all of the different, or the 3 parts of the demo that I've built. So nothing new there. On the server side, the important part is now here. You can see that we got rid of the dual write problem because everything the API server does is just write the message into the database. And the way how it gets informed about new messages is that we're running this polling interval at 1 second, and we are requesting all the messages that have been created in the last second. And for each message that we find, we're emitting this event to all the subscribed clients. So that's how polling works. And the problems with that really are that in a real application, you'll actually not only have a single polling query that's being executed every second. Instead, per user, you'll have a number of queries. So assume you have n users in your application. Every user will have n polling queries. If we think about how a real-world chat application would actually be built, every user has maybe a number of chat rooms that they are part of. They have a number of direct messages that they are sending with other users. And so we need individual polling queries for each of these. And that just gets very fast, very resource intensive with growing traffic. So the pros of this approach are that it's easy to understand, we don't need any additional infrastructure, and we don't have this dual write problem because all updates are actually coming directly from the database. The cons is just that it gets very, very resource intensive when you want to scale this to multiple users. Also, I mean, in my demo, I just had 1 query, but it was also implemented in a very, very naive way. In reality, you'll want to implement some diffing logic. You want to optimize these queries, maybe batch them. That gets complex really fast. And if we think about it as engineers, I think the ambition for ourselves should be that we find the right tool for the job. And for polling for a real-time application, it really doesn't feel like the right tool for the job that we ask the database every second, or if you want to simulate actual real-time, every 10th of a second maybe for new updates. So polling also really doesn't cut it. So the proper way how to deal with this problem is that we need to add extra infrastructure to our architecture. And what comes to mind there are message queuing systems like Kafka, RabbitMQ, or Debezium. With this infrastructure, we're adding this additional component, a message queue. And if we're taking the naive publish-subscribe approach here, it will look something like this, where at first the API server subscribes to the message queue to get informed about new events. Then we start again by Alice sending a new message via her WebSocket connection to the API server. The API server, it publishes, first writes the message to the database, then publishes a new event to our message queue. It receives the event because it's subscribed to that as well. And finally, it broadcasts the message to all the connected clients. That's how it works with a message queue. The pro is that now it's horizontally scalable. We can actually have multiple API server instances because they all are subscribed to the message queue. But we do have the operational overhead of maintaining and setting up additional infrastructure. We still have the dual write problem. And this is illustrated here, actually. The dual write problem means that, again, we have two operations without a transactional context. The first one is we write it into the database. The second one is we publish this event to Kafka. And if we do that, if one of these fails, it's very difficult to recover from this. And you don't want to start writing your own application layer logic for recovery. You really want to find a better approach to that. So how do we get rid of the dual write problem? The answer to that is called change data capture. Change data capture is based on the idea of unidirectional data flow that just eliminates this problem of the dual write problem altogether. Here is what it looks like. The architecture in terms of the components that are involved still looks similar, but if you look at how the data flows, it goes from the API server to the database. The database is now responsible for publishing the events to our message queue, and the message queue still broadcasts the event to all the subscribed clients, in this case, the API servers. So how does this look like in practice? Alice sends her message to the API server. It writes it into the database. The database sends the create event to our CDC server. The CDC server broadcasts the event to all the subscribed clients, all the API servers. And from there, the message arrives back at the subscribed front-end clients. What's the catch with CDC? If I have to boil it down, it really is this. It's really complicated to implement this yourself. You're getting deep into distributed systems territory, and this is just something that, like some companies have entire teams dedicated to working on. And if you're just a small startup or an agency or a company building products, then this is really not where you want to spend your time. The folks at Red Hat, they built a tool called Debezium, and Debezium really is the industry standard to implement change data capture CDC. And this is the getting started tutorial for Debezium. It uses Docker, it uses MySQL, it uses Kafka, it uses Apache Zookeeper, Podman, and Debezium, and you all have to set this up, and this is very, very complicated. So Debezium isn't a lot easier than just CDC itself. It still is a lot of operational overhead. It still is a lot of maintenance. And if you're just a small team or if you just want to save the work, then this is also not the approach you want to take. At Prisma, we just built Prisma Pulse. Pulse is also built on the idea of unidirectional data flow. In fact, it uses Debezium under the hood. So we're actually running the Debezium instance for you, but you save all the overhead of operating and maintaining it. It sends type-safe database changes into your application, and it's fairly easy to understand and set up. All you need to do is you configure your database, you set up Pulse in the Prisma data platform, you install the Pulse extension for Prisma Client in your application, and you're ready to go to subscribe to events. This is all the code that you need for a subscription. You just tell which table you're interested in to subscribe to, and then you start an async iterator inside of your Node.js application, and you're ready to go to receive events. What does this look like in code? I'm just going to show you the last server file here. It looks fairly similar to before, except that this time we're using this Pulse extension. We're initializing it with an API key. And we don't have the dual write problem because everything we do is just write a message to the database. From there, it's being picked up when we subscribe to the chat, which we do here. Here we start the subscription. And then for every new event that is coming in, we're emitting it to all the front-end clients. Change data capture with Pulse is easy to use. It's horizontally scalable. You don't have the overhead of maintaining additional infrastructure. It ensures data consistency via the unidirectional data flow pattern using CDC under the hood. And one of the drawbacks, of course, it still needs that additional infrastructure. It comes at a cost. It is a commercial product, so it's not going to run for free. And one of the things is you also still have to wait a little bit. Right now, it's still in a private beta phase, so you have to sign up if you actually want to test it. But we're making great progress, and it'll be opened fairly soon. Let's recap. Building real-time applications comes with a lot of